display and flip. Okay, that would work. So Badanga will do the introduction. Yeah.
Oh, yes.
Okay, thank you. So we still have 1 minute to go.
How are you?
Good, good.
I don't see full screen yet. Are you trying that or?
Yes, I did, but apparently, let me see if I can get the full screen share. Because I can share only the window. Let me see. I think I can try to do this. Share screen. Whole screen, okay. Share. And then.
Yeah.
Yes.
Is that right?
That works, yes, that works.
Okay, so I think it's time. So let's welcome everyone. This is the second talk in the series of RIC BES Theory and Experiment online series. Today we have Professor Misha Stephanov from Department of Physics, University of Illinois at Chicago. His main area of research is theory of strong interaction, the force that holds the atomic nuclei together, and its applications such as physics of neutron stars and heavy ion collisions. He is also one of the main drivers of the DOE-sponsored Beam Energy Scan for Theory, BEST, a topical program where QCD critical point search at RIC is a main component. Today, the title of his talk is Critical Fluctuation Dynamics. So without any further delay, Professor Stephanov, please, the screen is yours. Talk is 60 minutes plus discussions.
Thank you, Binanga. I was asked to talk about critical fluctuations, in particular the dynamics of critical fluctuations, which has been a subject of recent developments. I will give a brief introduction into why we want to study fluctuations, in particular in the context of QCD critical point. I will outline the basic ideas which were developed about equilibrium fluctuations near the QCD critical point and how they can be used to discover it. And then I will go to my main topic, which is understanding the non-equilibrium dynamics, which is especially important in the context of heavy ion collisions. So what is the critical point? The critical point is a ubiquitous phenomenon in ordinary condensed matter. Almost all fluids, or probably all fluids that are known to man have a critical point, including the most ubiquitous liquid, which is water. This is the phase diagram. Critical point is an endpoint of the boiling transition. It's a transition or a phase separation line or phase coexistence line, depending on what phenomenon you are focusing on. It's an ending point which for water, for example, occurs at very high pressures and temperatures. At this point, the difference between the two phases disappear. And the question that we want to answer is there such a point in quantum chromodynamics? The way we understand today the phase diagram is best of the quantum chromodynamics or strongly interacting matter is in terms of this plot of temperature versus chemical potential. And we expect that, well, based on first principle lattice simulation, that zero chemical potential, that is no net baryon number asymmetry in the system, the transition is not a sharp first order phase transition. There is no phase separation here or phase coexistence, but rather a smooth transition from one phase to another, which we call crossover. However, even though lattice simulations are unable to reach to arbitrary chemical potentials, from many calculations in models of strong interactions or models of QCD, we expect that the phase separation will appear, or phase coexistence. That is, on the phase diagram, is represented by this first order phase transition line, and its beginning or its end, depending on which direction you approach, it is the critical point. How can we discover the critical point? Well, obviously there are two possible approaches. One is theoretical or first principle approach, which I have already mentioned, suffers from a problem which is known as a sign problem, which restricts its reliability or reliable calculations to zero chemical potential, where we know that the transition is a crossover as a result. And the second approach is experimental, based on heavy ion collisions. And both approaches have their own challenges. The latest simulations are suffering from the sign problem. Heavy ion collisions have a completely different challenge, which is they create systems which are not completely in equilibrium. And so studying critical phenomena in this situation is a different task. So what is the strategy? Well, the strategy based on the fact or the observation that is confirmed by the experiments is that the evolution of the fireball upon collision goes through several stages. And the main stage, which occurs after the initial collision and thermalization, is the expansion and cooling of the fireball, which can be described by a trajectory shown here in this white lines, which where the state of the system changes and can be described by temperature and chemical potential, tracing a trajectory on the phase diagram, which ends in a freeze out. The thermal state at freeze out is what experimentalists measure. And the main observation is that the position of that freeze out point on the phase diagram depends on the initial collision energy, which is here shown in white numbers in GeV. This is a square root of S of the two nuclei colliding. And changing the collision energy, which is experimentally adjustable, tunable parameter, one can scan the phase diagram. This is, for example, in yellow indicated the range of the phase 2 of beam energy scan at RIC, which is now underway. If the critical point is located in the range which is accessible by this scan, then we should be able to see its signatures. And the next part of the talk will be the discussion of what signatures we should be looking at. I should say that before I go to the discussion of non-equilibrium, I will start with a discussion where the basic assumption, a simplifying assumption, is that the heavy ion collisions creates a system which at freeze out is sufficiently close to equilibrium that we can study thermodynamics. This will be a first approximation. So the signatures that we are looking at are based on event-by-event fluctuations. Heavy ion collisions are different from condensed matter system in some way, but it's also similar. The heavy ion collisions create a fireball or a system which is large enough for thermodynamics to apply, so that we can use the concepts of temperature, chemical potential, and equation of state, but not yet too large, like in a condensed matter system, where the number of particles is astronomical. In heavy ion collisions, the number of particles is large, but not too large. And therefore, the fluctuations in different realizations of these states or events in heavy ion collisions are small enough that we could talk about equilibrium thermodynamics, but measurable. And this is, for example, how these fluctuations look like. You, if you attended last week's talks by my chairman, you would have seen a lot of examples. This is, for example, the event-by-event distribution of the net proton number in collisions at RIC, as measured by star. So now let me discuss what we expect from equilibrium fluctuation near QCD critical point. The basic theory of fluctuations was introduced by Einstein in 1910 in the attempt to describe the phenomenon of critical opalescence, which accompanies critical points at observation of critical points in condensed matter systems and liquids. And the idea is that the probability distribution of order parameter, or the quantity which fluctuates most near the phase transition, I will denote it by sigma. It could be density. Typically, in the case of liquids, it is a density. Is governed by the entropy as a function of that quantity. It's an exponential of the entropy, and in thermodynamic limit, when the volume is large, it's approximately Gaussian. This is a central limit theorem with a width which is inversely proportional to the square root of the volume. The critical point is special because the entropy at the critical point has a flat maximum. The second derivative at the maximum of the entropy at this point on this plot vanishes. And as a result, the measure of the magnitude of the fluctuation, so the variance of the order parameter delta sigma squared average, normalized appropriately to have a finite volume, infinite volume limit, is not finite, it diverges. That on its face seemed to violate the central limit theorem, which says that this quantity has to be finite in the infinite volume limit. And in order to understand why this happens, it's useful to think of why the probability distribution flattens at the top. Well, the simple explanation for that is one can obtain by looking at the probability distribution before and after the critical point as you go from the crossover side to the phase coexistence side of the critical point. At the crossover side, there's only one phase, so the probability distribution of the order parameter has one peak, and it has two peaks on the phase coexistence side. The system is either near one or the other, and in between, obviously, to transition smoothly from one to another, the probability has to flatten. So how could then the central limit theorem is violated? Now, this is a key question one needs to ask, and the answer is that the main assumption of that theorem is that the fluctuations is a result of the averaging of an infinitely many or very large proportional to volume uncorrelated contribution. And this is no longer true at the critical point because the correlation length increases and therefore fewer correlated subvolumes fit in the volume of the system. In fact, what happens at the critical point is that the variance of the distribution is, although still inversely proportional to the volume, grows as a square of the correlation length. This is one of the key features of the critical point, this divergence of fluctuations as you approach the critical point with correlation lengths, is a key to its search. Furthermore, as I already discussed just now, not only the distribution, the variance of the fluctuation becomes large, but also the distribution itself becomes less Gaussian. That is, can be quantified by measuring the non-Gaussian moments or cumulants of the distribution. Furthermore, those cumulants depend on the correlation lengths with a much steeper power of correlation lengths. For example, the quartic moment, kappa 4, scales with correlation lengths to the power 7. This is another, this is the main reason why experiments searching for the critical point are focusing on the dependence of quartic cumulant or kurtosis related to it on the collision energy. Moreover, unlike the width of the distribution, which must be always positive, the deviation from Gaussianity could have different signs. So the signs of the kurtosis could depend on where you are relative to the critical point on the phase diagram. For example, on this plot, which is a universal equation of state near a critical point in the Ising model universality class, which is a prototypical system in that universality class, in which QCD critical point is also expected to fall. This distribution of the sign of the kurtosis is represented of the quartic moment or cumulant is represented by color on this diagram. The axes here are reduced temperature, or the difference of temperature in the Ising model from the critical temperature, which is at 0, and that is a red dot, and the ordering of magnetic field H. So if you are on the crossover side of that transition where there is no phase coexistence, the force cumulant is negative, and one can understand this from this picture of this distribution. And if you are on the first of the side of that critical point, then the force cumulant is positive, and also positive in most of the phase diagram around the critical point. How does this translate into the QCD? Well, the mapping between the universal of the universal equation of state to QCD requires non-universal translation or mapping, which is approximately linear near the critical point between the variables magnetic field and reduced temperature of the Ising model and the temperature and chemical potential of QCD. So this mapping in principle is non-universal, and we will have to use experimental data, or hopefully at someday the latest data to determine its parameters. But we already know something about it, and there have been attempts to construct, well, they have been constructed a parametric equation of state, which could help us understand the results of the experiments in terms of this non-universal mapping. It was also understood that the angle between these two axes, this is essentially a magnetic field axis where the reduced temperature is fixed, or the temperature axis where the magnetic field is fixed, are not orthogonal. Moreover, the angle between them vanishes in the chiral limit. So we have all the reasons to expect that this angle is rather small. And there are very non-trivial consequences of both of these slopes. Well, first of all, this slope in QCD or in any liquid gas phase transition, the slope of temperature axis is the same as the first order line. This is universal, but the slope of the other line is non-universal and depends on the mixing between the temperature and magnetic field in this mapping. And it has a very non-trivial effects on the phase diagram around the critical point, which I will not talk about today because I'm focusing on non-equilibrium fluctuations. Furthermore, the experiments do not directly measure the order parameter. They measure quantities like in this plot, which are the numbers of particles or multiplicities of particles of different charges and other quantum numbers. It is possible to relate the fluctuations of the order parameter to the fluctuations of these quantities, and all we need to know for the purpose of this talk is that to leading order, this relationship is basically a linear relationship. There is a baseline value for all cumulants, which is essentially Poisson value. In the case of multiplicities, it's just average multiplicity. So what should we expect as we scan the phase diagram, changing the collision energy, and the freeze out point moves along this dashed line on this plot? Well, as we already discussed, the initial approach to the critical point from the crossover side is characterized by negative contribution, critical contribution to the fourth moment or kurtosis of the fluctuations, and that should be reflected by the negative deviation from a baseline, whatever that baseline is. There may be other contribution to fluctuations besides critical. It could be a Poisson baseline, like in this picture. Which has then to turn over, become positive as we enter this blue region, and then as we exit it away from the critical point, it should fall down again. And the experimental data collected at a beam energy scan phase 1 has a suggestive dependence like this. We see these characteristic features. There is a negative dip. There is a positive raise, and we do not see yet if there is a fall at higher baryon chemical or smaller square root of S or larger baryon chemical potential. This plot is a preliminary data, and I only chose it because this is the only plot I found where the data is plotted versus the chemical potential at freeze out. The latest data, which you saw last week, presented by Bidanga, looks like this. Obviously, the direction of square root of S axis now is reversed, and so you start from large square root of S, and as you decrease it in the beam energy scan, we have a negative dip, which is followed by the rise. And the goal of beam energy scan 2 is to reduce the error bias, obviously, on this points to confirm the rise and to extend this dependence to smaller collision energy or large chemical potential to see if we could observe the fall of that peak back to the baseline. And that is in particular the purpose of the star fixed target program, which allow us to reach to smaller beam energies and larger chemical potentials. So this is the state of the field at the point. Now I will switch to the new developments of understanding the non-equilibrium dynamics of fluctuations. I should say there have been several directions in this in these fields, and I will somewhat perhaps selfishly focus on the developments which I contributed myself most and followed closely. The point I want to emphasize is that non-equilibrium physics is especially essential near the critical point. And the reason, which will be clear more quantitatively later, is simple. The significance of non-equilibrium effects is due to the competition between the two time scales, the scale of the expansion of the system, which is relatively long in the heavy ion collisions, which allows us to make this assumption of approximate thermal equilibrium, and the microscopic scale of relaxation rate or time of the system to equilibrium. And that relaxation rate or relaxation time diverges at the critical point. So the system takes longer and longer to equilibrate, and it falls further and further away from equilibrium. And this challenge of understanding of how fluctuations behave in this situation, in this competition, is been taken up by the B-manager scan theory collaboration, in which I am a part of, which attempts to build a quantitative theoretical framework describing fluctuation signatures for comparison with experiment. And the strategy is straightforward. We start with a parameterized equation or family of equation of states with unknown position and other variables of the critical point. And then we will use this equation of state in the hydrodynamic simulations, which could be then, the results of which, after freeze out and particularization, could be compared with experiment to determine and constrain the parameters of the critical point. And the ingredient I will describe in this talk is the stochastic, is the dynamical description of fluctuations. The most common way of describing fluctuations in hydrodynamics is stochastic hydrodynamics. This is a textbook approach introduced by Landau and Lifshitz. It's useful to start from that to understand the approach that I'm going to be using. Let me go back to the fundamentals of hydrodynamics, which is, I will phrase it as a conservation equation for quantities, for conserved quantities, such as energy density, charge density, or even momentum density. So this equation, which we usually write this in covariant form, in general, all hydrodynamic equations have this following form, in which the rate of the evolution of a conserved density is equal to the amount of flux which exits the given, let's say, volume of the system. So it's the divergence of the flux, which is a function of that quantity, or quantities, if there are more than one conserved quantity. This quantities is usually, traditionally, are viewed as averaged quantities. However, to understand the hydrodynamics better and the role of fluctuations, one should think of them as stochastic variables, because the way that they are obtained is by averaging of conserved densities or local quantum operators which correspond to these conserved densities over hydrodynamic cells, which are large compared to microscopic scale. So P is much bigger than microscopic scale, but still finite and smaller than the typical hydrodynamic scale, which is a scale of gradients in the system. That way, we can obtain the quantity which is not quite deterministic, in a sense that different ensembles or realization of the system will have different value for that averaging. And the fluctuation of that average is essentially classical and can be described by stochastic equations with noise. So in other words, the rate of the quantity, even stochastic quantity, still obeys conservation equation, but now the flux can fluctuate. So this noise, which Landau-Lifshitz adds in this equation, is what causes this equation to become stochastic equation. And linearized version of this equation is a textbook in non-relativistic stochastic hydrodynamics and has been also studied in the context of heavy ion collisions. The most interesting, especially in the context that we are discussing, are the nonlinearities in this equation. And those nonlinearities cause, well, the equations of hydrodynamics are inherently nonlinear. Those nonlinearities, together with the fact that the noise, since its cause is microscopic, is essentially point-like on the hydrodynamic scales, and that leads to ultraviolet divergences, very similar to the way that products of operators in the quantum field theory cause ultraviolet divergences, which require additional effort, such as renormalization, in order to properly define this theory. And in numerical simulations of stochastic hydrodynamics manifest themselves in the cutoff dependence of the results on the choice of the size of the hydrodynamic cell, which of course is unphysical. And that motivates, this is one of the motivations of pursuing a deterministic approach, the approach in which all the quantities or all the equations are actually deterministic equations, but the variables now include quantities characterizing fluctuations as well as the mean value. So we still have the average of this quantity, conserved density psi, as well as a two-point function of that quantity. In principle, this could be extended to higher point functions or higher order correlators. So this is the quantity which measures the correlation between G, measures the correlation between the stochastic variable in one point and stochastic variable in another point. So it's a two-point function. And the equation equations, or the system of equations which emerges, which governs the behavior of both the mean values or the average quantities and the fluctuations, have the following form. The evolution for the mean value is still given by the conservation equation. So the rate of change is proportional to the flux or the divergence of the flux. However, that flux now depends not only on the mean value of the fluctuation, but also on the magnitude or the correlation function G. While the correlation function G itself obeys a relaxation equation. It's not a conserved quantity. It relaxes to its equilibrium value, which we described on the previous part of the talk. This approach has been recently applied in the context of the heavy ion collisions, or developed by several groups, starting with Akamatsu et al. And Martinez and Schaefer, and have been extended in our work for arbitrary relativistic flow. And I will discuss this in more detail today. And of course, there is an earlier non-relativistic context in which this approach was well developed in the 1970s. The advantage of the deterministic equations, as I already indicated, and the motivation for this is that the infinite noise problem, the problem which is caused by the fact that in order to describe a point-like noise, one has to take the limit in which the magnitude of the noise is infinite. So this infinite noise problem, which causes ultraviolet divergences, can be dealt with analytically in a procedure which is very similar to the ultraviolet normalization in the field theory. Vidanga, can you hear me? Yes,
Yes.
Just wanted to double check that my connection is stable. Okay, so before I go to a more general approach, let me describe the approach which is similar to, well, which is essentially a deterministic approach, which is specifically tailored to fluctuation dynamics near the critical point, which is also the main subject of my talk. The reason that it is simpler is than the most general approach is that near the critical point, one mode of fluctuations is dominant. There's the fluctuations of the order parameter, and therefore this additional mode that we need to introduce, the two-point function, is only needed for that particular mode of the fluctuation. So extending hydrodynamics by adding additional mode, which is non-hydrodynamic, which is the correlation function of a slow mode, is, we refer to it as hydro plus. So fluctuation dynamics near the critical point requires two main ingredients, obviously. First, we need to be able to describe critical fluctuations, that is fluctuations whose correlation length diverges. And the most important consequence of this is that the time of relaxation of the system to its equilibrium state diverges. Near the critical point, this divergence is universal, the power divergence, and the power is approximately 3 for the universality class that we're talking about. We'll see in a second how this arises. Because the system relaxes slowly, that in particular leads to the divergence of the bulk viscosity, which is typically proportional to the relaxation time of the slowest mode, which in this case diverges. And that leads to the breakdown in hydrodynamics when you approach the critical point, because the relaxation rate becomes large, or correspondingly kinetic coefficients diverge. And both of these properties near the critical point are described by the same object. It is the two-point function of the slowest hydrodynamic mode, which at the critical point is the ratio, well, not only the critical point, but especially the critical point, is the ratio of entropy density to conserved charge density. This is the quantity which doesn't change in the fluctuations of the sound. So it doesn't mix with the sound, and therefore it's the slowest mode. This two-point function, I introduced the variable m to denote the ratio of entropy to charge density, and the fluctuations of m. This two-point function is the additional variable which was denoted g on the previous transparency. As I already said, if one does not include this mode, hydrodynamics would break down near the critical point. However, introduction of this mode could actually describe that process of the breakdown, extending the range of applicability of hydrodynamics. So this two-point function is can be represented systematically as in terms of its Wigner transform, which is a Fourier transform with respect to separation between these 2 points. The reason that it works, and it's similar to the way that the Wigner function becomes a particle distribution function in the kinetic theory, is that because of the separation of scales. Because there are 2 points, there are essentially 2 distinct dependencies of this function. There is dependence on the midpoint, x plus x minus divided by 2, which is very slow, characterized by hydrodynamic scales, or the scales of homogeneity, which is long. And another scale, which is a scale, characteristic scale of the fluctuation wavelengths. And it's determined by the typical fall off of this correlation function with the separation. And that scale is much smaller. Remember that equilibrium, that scale is essentially 0. So when we are close to equilibrium, we see that separation of scale. And that makes the Wigner transform a very convenient representation of this function. In order to describe the dynamics of this quantity, we consider the extended entropy. Essentially, now that we have additional degree of freedom, or a set of additional degrees of freedom characterized by wave number or wave vector q, we could consider the entropy as a function of this extended set of degrees of freedom. The usual hydrodynamic densities like energy and charge density, as well as this additional modes, fluctuations modes. One can calculate that entropy from first principle just by using that formula for the entropy of a given ensemble of the system, and find additional contribution due to that deviation of that fluctuation variable phi q from equilibrium, which is denoted by phi q bar. One can see that when phi q is equal to its equilibrium value, this term vanishes and we get usual thermodynamic entropy, while at any deviation from equilibrium, this contribution is negative. The entropy is always smaller in non-equilibrium state. Basically because we know more about the system than about equilibrium system. In equilibrium system, the value of the fluctuations is given in terms of the values of epsilon n. It does not constitute additional information. Another way to understand this contribution is to remember that the entropy is a logarithm of the number of states in the ensemble. And that number of states depends on how wide the probability distribution, and phi q is essentially the width of this distribution. And therefore, there is this term here, which is proportional to log of phi q, which represents the spread of the distribution, probability distribution in this configuration space of the system. And there is additional term which balances it, because the further away we are from equilibrium, the more is the suppression of the entropy, and the maximum is achieved when the fluctuations are in equilibrium. And the kinetic equation which describes the relaxation of this additional hydro plus fluctuation mode is essentially a relaxation equation, which I write here in the Onsager form, where pi q is essentially thermodynamic force. It's a derivative of the entropy with respect to the corresponding mode. Gamma is the Onsager coefficient, or the relaxation coefficient, which can be calculated in the models of critical behavior. In this particular case, it's a model H. Its dependence on Q is non-trivial, but what is essential here is that because it's a fluctuation, it's a two-point function of a conserved quantity, its relaxation rate is proportional to the square of the moment. It's essentially diffusion squared. That's why there's a factor of 2. And D is a diffusion coefficient for the system. So the typical fluctuation which needs to, or the longest fluctuation which needs to relax in order for the system to be considered of equilibrium is a fluctuation at a scale of correlation length. So Q for the inverse psi is the determines the typical relaxation rate, and one can see that that means that the larger the correlation length, the slower the relaxation rate to the system. Furthermore, near the critical point, because of the singularities in the equation of state and kinetic coefficients, the diffusion constant vanishes. It vanishes again with universal power, which is close to -1. So it's 1 over psi. So altogether, 1 over psi squared times 1 over psi gives us that result, which I already mentioned, that the relaxation rate of the system near equilibrium, near the critical point, is inversely proportional to the cube of the, or proportional to the cube of the correlation length. And that's essentially the phenomenon of the critical slowing down. It should be also understood that what is actually relaxing to equilibrium, which delays or slows down the system, is the magnitude of the fluctuations. And it is the slowness of this relaxation rate which leads to breakdown of hydrodynamics and necessitates the and which allows hydroplast to extend it closer to the critical point. So far I have discussed this specific case where one particular mode is the slowest, and one can focus on its relaxation to equilibrium in the dynamics, which leads us to hydroplast. However, if we want to consider more generally the evolution of fluctuations, including away from the critical point, we need to consider fluctuations or two-point functions at the first stage of this approach of all hydrodynamic quantities, which includes not only the entropy to charge density m, but also pressure and flow velocity. So I will collectively denote those this set of variables by phi. And therefore, we need to introduce a two-point function, which is matrix values, which corresponds to correlations between fluctuations of these variables. And in order to make this a relativistic theory, it is important to understand what does it mean to define an equal time correlator? What does equal time mean in relativistic hydro? Since we know that the equality of time at two separate points is a function of the inertial frame, which observer is using. And I will also describe how the issue of renormalization works in this generic approach. So let me first start with discussing how the equal time correlator is defined. Obviously, in the non-relativistic theory, there is no issue. Equal time is has absolute definition independent on the frame of reference, but in relativistic hydrodynamics, equal time depends on what frame we use. So we need to choose a frame. And that choice doesn't have to be the same in all points. And of course, the most natural, physically relevant frame in each point of the fluid is the co-moving frame, the frame characterized by the four-vector velocity four-vector u. So here I indicated by this vector. Now, equal time would correspond to 2 points which are in the plane perpendicular to this four-vector. So if we now look at another point where the velocity four-vector is different, so it points in a different direction in the four-dimensional space, the equal time will have different meaning. So the points which are equal time in this frame are not equal time in this. And if we want to compare or take a derivative of this function with respect to, let's say, the spatial space-time position of the midpoint, we have to take this into account. We cannot compare, we cannot fix the separation vector y between these 2 points, because this separation vector will separate points which are not equal time at a new point x, at x plus delta x. The way we do it is by boosting this separation vector by the same boost which takes u at one point to u at another, the velocity vector at another point. And after that boost, we then can compare the equal time correlation function in two points. Similarly, we can define such a derivative. We call this derivative confluent because it's adjusted by the flow of the fluid. If we want to compare 2 quantities, for example, which are not scalars, such as, for example, fluctuation of the flow velocity, which, because four-vector u is unit vector, so its variation has to be perpendicular to it, right? So we do not want to compare the velocity vector in one point, like in point x, to velocity vector in another point, x plus delta x, directly. Because what we want is to see how the quantity changes relative to the local rest frame of the fluid. So before we compare these two, we boost the velocity or the velocity fluctuation to the same frame in both cases. So in this case, I boost the flow fluctuations at point x plus delta x to the same velocity to the frame at point x, which is the rest frame, co-moving frame. And then I will compare the velocity fluctuation phi at point x with this boosted value. This is essentially the discretized definition of the confluent derivative. It is similar to covariant derivative, but it is different. Similarly, when we do the fluctuation correlator, we also want to correlate two values which are also boosted to the same point, which again, in a natural choice is a midpoint. As a result, in the calculus limit, when delta x goes to 0, we can define a confluent derivative, which is essentially takes into account these boosts through these connections, as well as the adjustment of the separation vector, which is also described by its own connection. After that, we take the Fourier transform of Wigner transform, Fourier transform with respect to the separation vector, and write the equation which this Wigner transform function satisfy. There's a lot of work involved in deriving those equations, and I keep appreciating the remarkable work which Shinan did, plowing through these calculations. And it is also remarkable that there are so many miraculous calculations which leads to the final result, which is extremely simple and physically intuitive. And I will just focus on that. So if we focus on longitudinal components, which are essentially the fluctuations of pressure and longitudinal component of the flow velocity at constant S over N, they obey the following equation upon normalization. This normalization is also non-trivial. If you look at this equation, it is essentially a kinetic equation for phonons moving in a background of flowing fluid. So locally the phonon propagates with the speed of sound, but the fluid itself propagates. So as a result, the phonon experience non-inertial forces. It doesn't propagate along a straight line. And these inertial forces have very well easily identifiable components. There is acceleration force proportional to acceleration of the fluid. There is a Coriolis force proportional to verticity of the fluid. There is a Hubble force which changes, for example, the wave number of the phonon. For example, redshifts the phonon when the system expands. And there is a usual force, which is a gradient of the energy due to the change of the equation of state and correspondingly the speed of the sound. So this is the left-hand side. This is simply a Liouville operator for this kinetic equation. The right-hand side is evolution, is a relaxation term, which simply describes the relaxation of this distribution to the equilibrium Bose-Einstein distribution, which is correctly normalized as well. So this was the evolution equation for the longitudinal component, so the sound correlations. There are other modes, and the ones which do not average out are the entropy velocity and velocity fluctuations, which obey equations which I write in a similar form, where the left-hand side is also a Liouville operator, but with no propagation. The velocity and the forces acting on quote-unquote particle described by this phase space distribution are zero, so there is no propagation, but there is a diffusion, and the relaxation of this distribution function to the equilibrium values, divergent for entropy correlation, and zero for example, the mixed one. And there are additional terms which proportional to the gradient of the background flow, which mix these different two-point functions. Near the critical point, the slowest relaxation rate is in the first equation, gamma lambda. And if you focus on the slowest mode, this mode, which we denoted MMM, is a two-point function of this variable M, entropy over charge, is decoupling. It decouples, and its evolution equation essentially coincides with the equation of Hydra plus in a very non-trivial way, as we also find out. However, additional modes which we introduce, which mix with these modes and which are faster, but still slower than other non-hydrodynamic modes, allow us to extend the applicability region of hydrodynamics to even shorter distances or higher frequencies. The breakdown of Hydra plus occurs essentially because the conductivity is frequency dependent, and the frequency dependence is enters at a point at a frequency which is equal to the relaxation rate of this additional mode, which is approximately inverse square of the correlation length. So at that point, the conductivity, which I denoted lambda, experiences frequency dependence, which means that the response, the Ohm's law, is no longer instantaneous. And that, of course, requires additional modes to describe it. And that's additional modes is what this extension, which involves additional modes, which we call Hydra plus, introduces. Finally, let me discuss the issue of renormalization. The simple way to understand it is to notice that if we take when we write the average equation or the evolution for the average thermodynamic quantities, which involves, for example, the evolution of T mu nu, the stress energy tensor, and expand it to quadratic order in fluctuations, upon average, we will have terms which are proportional to the average of the product of the fluctuation in the same point. That, in terms of the Wigner function, is the integral. And this integral diverges. And it's easy to understand it because in equilibrium, this two-point function is a delta function in space. And therefore, at a separation equal to 0, which is where we need to evaluate it, it is simply doesn't exist, it's infinite. So, however, one could separate this divergence and identify these divergent contributions to the non-fluctuating terms in the hydrodynamic in this expansion. So if we look at the Wigner function, delta function means that the Wigner function at large Q is a constant. So it saturates at some constant value, which is determined by fluctuation dissipation theorem, typically is proportional to temperature. However, it deviates at some scale from the term dependent on the frequency of the evolution. So at some separation scale or correspondingly wave vector Q scale, it deviates from 1. And this deviation can be described in powers of 1 over q squared. So the next term will be 1 over q squared, and the coefficient in front is essentially the gradient. And the next term is 1 over q to the fourth, which I can see is divergent. Sorry, is no longer divergent. It's a finite contribution. That's the contribution which is physical. So when we do the Fourier transform, we find that the leading divergence is cubic. So if we regularize it by introducing some wave vector cutoff lambda, it's cubic. The next is linear, and this term is non-local in space because it's non-analytic in Q. And one can see that if we return to where this two-point function came from averaging of the quadratic part of the fluctuations, if we substitute this into the expansion of average of T mu, we can see that the leading term can be absorbed in the normalization of pressure. The subleading term, which is linear divergence proportional to the gradients, can be absorbed in the normalization of viscous terms proportional to gradients. And the remaining part, which is non-analytic or non-local in gradients, cannot be absorbed anyway. And these are the physical contributions which remain. If we rewrite the equation in terms of renormalized pressure and normalized kinetic coefficients, then this equation is completely cutoff independent. That's the advantage of this deterministic approach. We do not need to deal with cutoff dependence and the cancellation of noise numerically. It's all done at analytic stage. Finally, let me come to my conclusion. There is still work to be done, in particular, as I discussed in the context of search for the critical point, we need to understand the evolution of non-Gaussian fluctuations, and that work is in progress. Of course, we, at the end of the day, have to connect this fluctuating hydra with freeze-out kinetics and implement in a full hydrodynamic code, which is also the work in progress within the past collaboration. And there are other interesting, both practical questions, such as first order phase transition, which we also have to confront in the context of the search for the critical point, as well as the connection to some theoretical formulations of hydrodynamics, which were developed recently based on Swinger-Keldysh approach. So to summarize, the fundamental question about QCD phase diagram, which we are trying to answer, is the existence of the critical point. And there are intriguing results from experiment, and there are more to come from both RIC and other experiments which are coming online in various places in the world. And there is a theoretical development which accompanies this, which is equilibrium dynamics of fluctuations, is that the magnitude of critical fluctuations is controlled by dynamical non-equilibrium effects.